While we're talking about multiplication, a very enlightening thing happens if we think of multiplication in terms of polar coordinates. Namely, take the two numbers which in polar coordinates are r1 comma theta 1 and r2 comma theta 2. Now again, remember from our Argonne diagram what it means to say that the complex number has polar coordinates r1 comma theta 1. Remember, the complex number is written in the form x plus iy. The x coordinate is r1 cosine theta 1. The y coordinate is r1 sine theta 1. At any rate, this product in terms of the standard notation, the x plus iy form, says we're multiplying these two numbers together. And using our rule for multiplication, multiplying term by term, and remembering that I squared is minus 1, observe that if we collect the terms here, and I'll leave the details for you to verify at your leisure, we wind up with r1, r2 being a common factor. The real part is r1, r2 times cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, the minus coming because I squared is minus 1. The imaginary part is r1, r2, sine theta 1, cosine theta 2, sine theta 2, cosine theta 1. If we now remember, theta is a real number. If we recall our trigonometric definitions, cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2 is cosine theta 1 plus theta 2. This expression is sine theta 1 plus theta 2. And remembering now that in polar form, what we're saying is what? This is the complex number whose magnitude is r1, r2, and whose argument is theta 1 plus theta 2. And putting these two steps together, what it says is that to multiply two complex numbers, the same definition of multiplication that we were using before, if we interpret this in terms of polar coordinates, says, look at, to multiply two complex numbers viewed as lengths, you simply do what? Multiply the two lengths to get the resulting length of the product and add the two arguments, the two angles. That's a rather interesting result. You see, for example, if we now want to think of the complex numbers as being vectors, this gives us a third vector product that we had never talked about before and which I'll reinforce in the learning exercises. The idea is that using this as a model, and here's another real application, why not define a new product of two vectors obtained by multiplying the two lengths and adding the two angles. And the point was that in our physical examples, there was really no motivation to invent this vector definition in the same way that we could define the dot product and the cross product for complex numbers, because after all, they are viewed as vectors in the plane. But again, we have no great practical application for this, so we don't bother doing it. By the way, just for kicks here, I thought you might enjoy the aside that this little interesting result explains why the product of two negative numbers happen to be positive. Remember, a negative number, if r has to see, a negative number lies on the real axis, and if r has to be positive, that means you're measuring in the direction of the negative x-axis, which means that the polar angle is 180 degrees. If you multiply two numbers whose angles are 180 degrees, if you add the two angles, you get what? 360 degrees? You see what I'm driving at here? In other words, if I multiply two numbers in polar form, each of whose angles is 180, the product will have the angle equal to 360. You see, and that puts you back on the positive real axis, and so you have such real interpretations as why, in terms of complex numbers, we can explain very nicely what it means for the product of two negatives to be a positive.